Hello, it's time for another physical sciences lesson. We've got an exciting lesson all about electrodynamics to deal with. And our focus today is on alternating current. Alternating current is something that you might be familiar with. In fact, it's probably how you're watching on a TV at the moment. It's what we find in our houses, how we cook, how we get lights. But have you thought about some important questions about alternating current? And here's the first one. Why is alternating current used to supply the country with electricity? Now, there's an interesting idea. Why is it alternating current, and why are we all using the same source of electricity? We've experienced times when that source isn't very reliable and we have to have load shedding or load reduction and we have blackouts. But normally we would find that everybody is plugged into the same system or grid and we're able to cook and watch TV or use a geyser. It's all because of alternating current. And we're going to find out a little bit more about it. So remember, the focus of electrodynamics is about electrical machines, the electric motor, which could be a direct current motor, where we use a split ring commutator. That word commutator is very important. The other machine, that machine takes electrical energy and makes mechanical energy out of it. We recognize that's not the only machine. The machine that we're interested that produces alternating current is going to be the one that takes mechanical energy and makes electrical energy from it. That's called the generator. And the type of generator that we're focusing on today is the one that produces alternating current. It has slip rings. And the whole relationship between this is driven by the idea of electromagnetic induction, Faraday's law. It's applying that relationship between force, current, and the magnetic field. And we're going to see exactly how that produces alternating current and the effect of that as we go through this. So alternating current, often called AC, what does it really mean? We recognize it all involves the principle of electromagnetic induction, which is related to Faraday's law. So in terms of Faraday's law, remember that it tells us that there's an induced EMF produced in a coil, and that is directly proportional to the rate of change of magnetic flux. Now, magnetic flux is the field passing through a perpendicular area. And we recognize that in the formula. Remember this, the field passing through an area that's perpendicular. And when we're wanting that area to be perpendicular, we correct for the perpendicularity of it by using that cos theta. And here's the equation that we're going to look at. Delta phi over delta t is going to be the EMF produced. So how does it work? Well, you'll remember that if you push a magnet into a coil, push it in and out, backwards and forwards, you will get an alternating current. The reading on the galvanometer swings backwards and forwards. It might swing to the one side as you push it in, as you pull it out, that swings to the other side. And so we have seen that when you move a magnet into a coil, you can get this sort of alternating reading on a galvanometer. But we could also spin the magnet, and we showed that we can do it like this in a simulation. If we spin the magnet, we've got a changing magnetic field that's cutting through the coil, and that is producing an induced EMF. And because it's a closed circuit, there'll be an induced current with it. So the little charges are moving backwards and forwards, alternating current. And then we have looked at the AC generator. We recognize here that we can turn it, and as we turn the armature within the field, we are going to get an alternating current. Now, what I want you to notice something in this situation is that the magnets are permanent. They are stationary. The field is permanent. It's not changing. And it's just the movement. The movement of the armature is also constant. It's not going to suddenly be fast one time and slow the other time, because we know the speed of rotation or the speed of movement relative to the magnetic field will change the induced EMF. So what is the thing that changes? Well, the only thing that is different as we turn this armature is the amount of area within this that's cutting through the field. And that is the thing that we're going to look on that produces for us the induced current in the coil. It not only changes direction as we're turning it, but it increases and decreases in strength. And as a result, we can get a graph that has an interesting shape. I'm sure you've seen this sort of shape in mathematics. It's, of course, a sine curve as I've drawn it here. It has a maximum value, it has a minimum value, and it has zeros at different points within the cycle. It's a cyclical term. And so we recognize that this current is changing direction and it's changing magnitude. And that's what makes it such an interesting thing to study. We've got to ask the question, why does it do that? But of course, we can't give the full explanation right now. We're just introducing the idea. And I think it's time that we just keep these ideas in our mind and we go and have a short break. After this, we'll explore the relationship between this graph and how that armature rotates within the coil. We'll see you after the break. Welcome back. I hope you've been thinking about alternating current and you've got some ideas buzzing around in your head. Well, let's go and have a look exactly what we're into as we take a look at this machine, the AC generator. It's sometimes also called an alternator. And as I mentioned to you, the thing that is fixed is the permanent magnetic field. So if instead of looking at this diagram, let's look at a diagram where we're looking from the end on. So in this case, it's like taking a cut through the alternator. We've got the north side of the magnet on the left-hand side, the south side on the right-hand side, and I've drawn some field lines that are connecting those together. The armature itself I've represented by this copper color as a dot, as a circle, and a circle over here, and just showing you that it's forming a coil. That line that is drawn between them is, if you imagine it's a coil. Now, at this point, the coil is moving down on this side because it's being pushed down by the handle, and it's being pushed up on this side. So at this point, let's just imagine that this is like a coil that is cutting through the magnetic field. Now, remember, we are only going to get an induced current if we can get the three things working together. The coil has to have motion, and it has to cut through the field lines. As it moves through those field lines, the field lines are going through an area that is perpendicular to the coil. So the coil is being cut by these field lines. And in this case, it's like it's being in a perpendicular situation. So the area is through this whole coil over here. Now, the trick to remember here is at this point, we've got everything perpendicular to each other. So the coil is moving in a way that is going to cut at 90 degrees to those field lines. The field lines are cutting perpendicular, and the angle between the area that those field lines cut through and the magnetic field is 90. So cos theta here is 0. And I want to just remind you about that the cos theta in this situation is equal to 0. So 0 degrees, because the field lines in the area are at 90 degrees. Okay, so in this situation, what we find is we get a maximum induced current. So that current coming out of the board, how do we know it's coming out? Do you remember? You've got to use the rule using one of your hands. Now this is a generator, so generally for a generator, we use the right hand rule. I'm putting my left hand so I don't get confused. So remember, you're going to go north to south, it's going down, so it's coming out. And that's the slap rule that we're using. So we go north to south, it's going up on this side, so it's going in. Of course, you can use the right-hand generator rule that has the FBI on it. Slap your thigh, you're in the FBI. Remember there, the thumb is for the motion, the first finger is for the field, and the second finger is for the current. So if we have the field in that direction, the motion up, the current is going to be in. And in this way, we go north to south with the field, the current, the motion is down, and I hope you can see that the second finger, the first finger is that way, the second finger is pointing out towards you. So that's why there's a dot and a cross in that position. Now remember that when it's on this side, it's coming out. At A, it was coming out, and at D, it's going in. So there's a motion in the circle, in this coil. That's a circular motion as it's moving through here. At this point, because it's cutting the field lines perpendicularly, that cos theta is 0, the area is a maximum, and the magnetic field is a maximum as well. In fact, the magnetic field doesn't change. The area of the coil doesn't really change either. It's a fixed amount, but it's the angle here that is the important one. It's a perpendicular angle. So I'm going to draw a dot to represent the current at that point. And I'm going to take this current when it's coming out at A, making A the negative terminal, linked to the slip ring, that's the negative terminal, and D is the positive because it's going in. So we'll remember that's the positive current at that point. Okay, so we've put the maximum current on the graph, much like we saw the earlier graph, and we're going to see what happens next. So a little while later, we're going to recognize that there's a change. A has slipped down, and it's now moving, and D is moving up. It's not cutting the field perpendicularly anymore. So there's an angle between the area. The cos theta now has to correct. This area part has got a little bit smaller. So what we recognize is the theta is no longer 0. It's got some value between 0 and 90. And so if we make the value of cos theta not 0, we recognize that the overall effect on the equation, which was phi is equal to BA cos theta, this theta is no longer 0. It's some value bigger than cos theta is bigger than 1. Less than 1. Cos theta is bigger than 0. The theta, the angle theta, is bigger than 0. So cos theta is less than 1. If cos theta is less than 1, then this is going to decrease. And if that decreases, we know E is directly proportional to delta phi. Of course, as it's moving, there's a change in the area. And so that's why we're going to get an induced current. We're going to get an induced EMF, and because it's a closed loop, we're going to get an induced current. Okay, so I think we're okay with that. So what do you predict is going to happen on the graph? Well, let's go and see. So there is our maximum value. We've just shown you that the EMF is going to be less. If the EMF is less, well, I reckon that we'll put a little dot over there to show that the current is still positive. Notice it's still positive. It hasn't changed. D is still the same as it was in the previous slide. So it's still positive, but it's got less. Because that cos theta, that angle between the perpendicular, cutting the field lines is no longer exactly 0 anymore. That angle has got a bit bigger. So we recognize that the value has got less. And so let's move it on a slide. What do you think is going to happen? D is now going to get into the vertical position. A is going to get into the vertical position. And that's exactly what we've got. Now notice here, D is moving parallel to the field lines. And A is moving parallel to the field lines. The area now, in terms of the perpendicular, is at 90. And cos of 90 is 0. And that's why there's no induced current. Okay? So in this position, what we can clearly say, and this is the important thing, even if you don't see the trig and you don't see that the angle's changed, recognize in this position, there's going to be no induced current. And what happens is we're going to find that the armature has to move over to the other side before there'll be a current induced again. And so the graph is going to get to a 0 point over there. So what is very important for you to see is the position of the armature in relation to the value on the graph. So when it's a vertical reading, it's going to be at 0. When it was the horizontal reading, it's a maximum. But notice in this point, these have all been positive values. Remember that D was where the current was going into the board, and A was where the current was coming out. In our next slide, we're going to see exactly what happens next. Is at this point, D is now with the current coming out. Current is coming out at D, and it's going in at A. So there's been a switch in current. It's no longer going in the same direction. As this thing is spinning, we're finding that the current is changing. Now, I haven't told you how fast it's spinning or how long this is taking. I know it might seem that it's taking a very long time for it to go from the horizontal to the vertical, and that's where we are, and it's now going over onto the other side. Okay? So it's gone through this process. This can happen very quickly. But what do you think is happening now? Well, the current in D was in and now it's out, so it must be a small negative value. So at that point, I can say, it's no longer, there is a current going in, it's not the maximum yet, there's still an angle between the coil and the field lines, the area isn't perpendicular, so we're recognizing that the cos theta here is a value that is not 0. And so we go to the next point and we see we're back into this situation where it's horizontal. Now the coil is cutting perpendicularly to the field lines. The area is at a maximum. Cos theta is 0, and we've reached a negative minimum. So that's your minimum value there. Now, as this rotates around, notice that D is going to come into this position. What value do you think we're going to get? Well, if you said it was a negative value, you'd be correct, but it's not more negative than the minimum. So it's gone over, and it's now coming back to the original position. It's coming back to its position back over here. And you'll see it's got to go through the 0 point first of all. So at this point, we've still got a negative current because D the current is coming out. At A, the current is going in. We're heading back to that line, and we'll get it when it gets to the vertical position. Notice when it's in the vertical position, current is 0. Okay, so please take note of that very carefully. Now, what do you think is going to happen when A gets closer to the North Pole, where it started from? Well, obviously, that's absolutely right. When A was close to the North Pole, there was a positive current. So the current is going to come out of A. It's going to go in at D, and we're going to get a positive reading on the current. So the next thing that if it moves over, there you see that it's going to move across, and we're going to get the current increasing over here. So in this situation, we've got an increasing current taking place, and we recognize that we're building up to that maximum position once again. And so Let's have a look. There we go. We've got the current back at the maximum. And so I'm going to show you what the graph now looks like. So, and you can see that this graph, I've traced through the whole region, and you can see that it's following a pattern. The pattern is not a sine curve now, but this is more like a cos graph. And what we're recognizing at different points, and I'd like you to take note of this, at different points on these graphs, the position of the coil. At this position, the coil was horizontal. At this position, the coil was down like that. At this position, over here where it was 0, the coil was in that position like that. Then it started to move the other way. So it's moved down on this side, it's now moving in that direction, and then it reached a maximum at that position, and now it starts to move the other way. And you can see that what's happening here, it's crossed over. And so it was moving up on the one side, down on the other. It's going to carry on. It's going to be the other way there. And in this position, it's going to be that way. In this position, it's going to be that way. And back over here, it's back into the 0 position. Now, these type of questions are often asked. So please make sure you understand how they link together. You know what? The examiner can be quite tricky. They can say to you, well, let's not start at the position where it's horizontal. Let's start where the coil is in that position. The coil is in that vertical position. You need to remember that when the coil is vertical, then the current is 0. But when the coil is horizontal, the current is a maximum. And if you understand that, and you can follow that and learn that, you won't have a problem with alternating current. What you need to do, though, is to make sure you identify where the graph is going to start. So if I'm starting at 0, I'm not going to have a cos graph. In fact, if the line was like that, I'm going to have a situation, if I'm starting over there, the graph is going to look something like this. At a maximum, at a horizontal position, a vertical position like that, it's going to be your sine graph. Whereas over here, I started with a horizontal position. So it started at a maximum. Let's take a more detailed look and zoom in on the sine graph. I've got a drawing here of a more accurate sine graph, and it's got some interesting data on it. I want you to take a careful look at it. What do you notice? Well, we recognize that the one thing that it's got is some values for time on it. And those are very short times. In fact, this is giving you an indication of how quickly the generators in a power station actually spin. They spin incredibly quickly. One cycle in 0.02 seconds. That means there are 50 cycles in 1 second. We say that means that the frequency of this alternating current is 50 hertz. Let's get going with our investigation into alternating current. So what we've discovered so far is that when we use a generator, it produces alternating currents, and that will always have slip rings. Now that's an important feature. What you need to recognize is that you're actually, when you're using an AC generator, you're using mechanical energy over here. And the mechanical energy is being transferred into some form of electrical energy. And that's really useful. We recognize there's lots to know about the generator and how it works and why it works, but what are the advantages of using this sort of generator? Well, we know that it certainly has advantages over using batteries, electrochemical cells, because those electrochemical cells, well, they'll run out. The internal resistance will build up and the batteries will go flat. And so it's not sustainable to do that. I suppose we could produce direct current using a different type of generator, not an alternating generator. In fact, we can use a direct current generator. How would that be not as advantageous as this one? Well, the advantage to the alternating current generator is that it's safe to transfer electricity over a long distance. Now, usually we have power stations that are burning coal or burning gas, and we don't want those in the middle of a city. There might even be nuclear power stations, or there might be hydroelectric dams that are quite a distance away from the city. And so you have to take the electricity that's generated in these positions, in these places, and you have to transfer it closer to where everyone is living. And the secret of why we like alternating current is because it's easy to manipulate. And although we don't need to study and understand the process, what you need to understand is that if we've got alternating current in a coil and we bring another coil next to it, there will be a change in magnetic flux, and so that secondary coil is going to have an induced current in it. And that is the process of transforming. So a transformer, which you might go past if you're living in the city, you might see there are substations and there are transformers. Alternating current is easy to transform because it's changing. And because there's a changing electric field, strength of electric field, there'll be a change in magnetic field, and that will induce a current in the transformer. And so there are ways to make the current from the power station be transformed into a high voltage current, high voltage and low current process at the power station. And so in those grid lines that you see strewn across the country, we find that we've got high voltage lines and they're bringing a low current. The reason for that is we recognize that energy is lost when the current is high. Now, when you come to the city and you've got lots of houses, we can divide the current to make it smaller. So every house is in parallel with the house next door. The potential difference is the same. So we can use a low potential difference, high current, split the current into all the dwelling places, and in that way, we're able to use it safely. So in a city, we have a step down transformer that is used for the city, and we use a lower voltage and a higher current that gets divided by each of the places that it's going to, each of the houses that it's going to. And so we recognize nobody's going to get hurt because the individual supplies, the endpoints, the current and the voltage are controlled. And so these are the advantages. The fact that we can distribute very easily, we can distribute safely, and we can distribute without energy loss. Now, as I've been talking about current and voltage, there's obviously a relationship between them. And I'd like to just take a look at that relationship by looking again at our graph. So there's an interesting idea here, and that is that we've got the time that I've indicated before, but we've got an ampere reading of current. And 15 amps is quite a lot of current that is being distributed. But recognize that that's not the maximum. So the maximum current happens at that point. And we would say that would be called Imax. Now, what could we do if we were saying, well, this is alternating current. I want the equivalent of this to run a machine, and I know that it can run a machine on DC, direct current, and use up 2 amps. So how can I work out? Because 2 amps might be there and there and there and there, but how do I know what the 2 amps is? What's this overall change of current going to give me? Well, we can't really even do an average, because if we take all these values and we add them up, and we take all these values and we add them up and we add them together, we'll get 0. And clearly that's not very helpful. So we've got to do something a little bit cleverer. And the mathematicians or statisticians help us with this. So the first thing they do is they say, well, let's square these values. Now, if you square anything that's negative, it'll become positive. So it'll flip over. So the squared graph would look something like that. And we can now say, we've got the square, but we don't want the square. So what we can do now is to get the average and say, well, let's add these together and then let's take the square root of them. And so if we take these and add them together and divide by 2, so we take all of these values together, so we take I squared and we take 2 because we're getting an average, because we've got the values, minimum, max, and then we'll say, well, let's take the square root of this whole thing. And if we do that, then we'll get I, that's on its own, over the square root of 2. And that is called the I root mean square. Now, that's a very important value. And we've got an equation for it where we say Imax is that. This is the average value for current. It's the IRMS value. And whenever you get a machine and they say this is what the current it can manage, it's the IRMS. And in the same way, we can get voltage. And the voltage oscillates just the same as current, because voltage and current are related. Remember, power is equal to V times I. And we know even in Ohm's law that voltage and current are related. They're directly proportional to each other. So if the current is high, the voltage will be high. When the current is 0, the voltage will be 0. And so we've sketched on this graph the voltage. But notice something. Voltage potential difference. We recognize that this is more than one cycle. This is 1.5 cycles, so please take note of it. Take note as well that this value is 220 volts. That is in fact the value of VRMS under our normal situations. The Vmax is the maximum value, and it's slightly more. It's about 311, if I remember correctly, but we'll be able to do a calculation to show that. In the same way as we had IRMS, we've got VRMS over here, where we're looking at the average value for the voltage that is produced for alternating current. So please remember the difference between these and make sure that you're following that very carefully. Now, I mentioned power just now, and I think it's an important thing to recognize that power gives us a way to do some calculations, further calculations. And so I just want to highlight this for you. We know that power is the product of current and voltage, but over here, average power, which is always the thing that is given on an instrument. This is the rating of a machine. It's called the rating. So it will say to you that this is a 15-watt instrument. Well, that's the average power. And the average power is found by multiplying IRMS by VRMS. And if you do that, you'll see that it comes out to root 2 multiplied by root 2 is going to give you a half, and then it's going to be Imax times Vmax. And that's quite a useful formula to recognize. And of course, we can use the other power relations that you've used for DC. You just need to recognize here that average power is not affected by resistance. Resistance is going to stay the same. So it's I squared RMS and V squared RMS that is going to give you the workings for average power. And so remember here that this is the same relationship or type of relationship that we get for any ordinary circuit. So having introduced you to these equations And this relationship between current, potential difference, and power, you know what? I think it's time to apply that knowledge. And so before we get into doing those sort of calculations, why don't you have a short break, get a pen and paper out so you can follow along as we try and solve some problems using these equations. We'll see you in a short while. Welcome back, everyone. I hope you've got your pen and paper ready and you've got a calculator on the side as well, and you're ready to solve some questions on alternating current. Guys, there are lots of different types of exam questions. Some might ask you about, is there a slip ring? Is there a split ring commutator in the machine? But these are the calculation questions that you might get. So please make sure that you prepare for them and that you do a fair amount of practice. So let's get ready to do that. So the first thing we're going to do is just to read the question very carefully. We say lights in most households are connected in parallel. And that's the beauty of the grid. The houses in the houses, everything's in parallel, and between houses, everything's in parallel. So we've got a whole parallel grid system. So we know we can supply constant voltage across the whole board. So when we've got two light bulbs, they are rated 100 watt, 220 volt. Now remember that that is a VRMS value, and this is an average power. The ratings are always the average. They're not the peak. So again, this would be the average power, and that would be the VRMS. And we're told they're connected to an AC of RMS value, and they've given it to you there. That is in fact the RMS value, the 220. But you can take it, if you see it on a machine, that's the RMS value. They don't have to tell you that. However, there's a fuse in the circuit. We're going to look at the circuit diagram now that gives a maximum current of 10 amps. Now remember, a fuse is a device that if a current greater than 10 amps passes or tries to pass through this thin piece of wire, it will overheat and it will burn, and the circuit will break and everything will go off. So it is definitely not the RMS value. The fuse value is a peak value. In fact, it might be slightly, it might be exactly the peak, but might be slightly higher just to protect things. You don't want it to go over the peak, okay? But you don't want every time it hits the peak for the fuse to break, so it'll be a safety mechanism. So here is our little diagram. Recognize that's the source. This symbol here, the circle with the sine wave in it, is going to be your AC supply. And we recognize that that value of 220 volts is your RMS, your root mean square value for your voltage. This is your one light bulb, and that's your second light bulb, and notice they're connected in parallel. And here's your fuse, telling us it can't get greater than 10 amps into this whole circuit. So remember that when you plug things in parallel, the overall current that is being drawn can increase because the resistance is decreasing. So we need to be careful not to plug too many things in parallel. So that's why the fuse is there, to protect the devices so that they don't exceed the current, we don't draw too much current. So let's get into the first question. It says calculate the peak voltage of the source. So what's the important information? Well, the important information is that RMS value for the voltage is 220 volts. So I've summarized the information here, the AC source, so we can say the VRMS is equal to 220 volts. And what we're asked to find is Vmax, the peak voltage. Now, I'm sure you are quite familiar that these formula are on the data sheet. And you need to read the formula from the data sheet and write them down exactly as they are on the data sheet. Don't try and be clever, just write them down from the data sheet. So even though we know that's what we're trying to find, let's write down the formula from the data sheet. And the formula on the data sheet will say Vrms is equal to Vmax divided by the square root of 2. And what's the next thing you need to do? This is really straightforward. We have to substitute the values into the equation. Now, don't change the subject of the formula, because if you don't substitute incorrectly, you will lose all the marks. You have to substitute into this part of the equation. So we're going to say 220 is equal to Vmax divided by root 2. And that means that Vmax is going to equal to 220 multiplied by the root of 2. And so let's just pull up the calculator. And let's plug the values in. So the first thing I'm going to do is I'm going to say, let's put the root of 2 in. So we're going to say root 2 multiplied by, let's put our values in. We're going to say the root of 2 multiplied by 220, and that will give us a value of 311.13. So let's write that down. We can say the Vmax is equal to 31113 volts. So there we have it. We have seen exactly what the peak voltage is. And that explains why when we looked at the graph, we found that it was bigger than 220. It was, and I said about 311, I think I put that down as we looked at it, but now we can confirm it. 311 is the peak voltage. Next part of the question. So what we're asked to do here is to calculate the resistance of the 100-watt light bulb when operating under optimal conditions. And the optimal conditions simply mean it's a 100-watt light bulb that operates at a Vrms equal to 220 volts. If you happen to use, or in another country, and you weren't using the Vrms of 220, 240, or 110, these are all used in other parts of the world, then this device wouldn't work properly, or it would work at a different resistance. So we need to be able to work out the resistance at the optimal conditions. So let's go and remember that if we're looking at this situation, we want resistance, we have to use a power equation. So we're either going to use that power, average power, is equal to I squared RMS times the resistance. We haven't got I squared RMS. Yes, you could work it out, but we're not going to. We've been given V squared, we've given VRMS, so it's appropriate that we choose that equation. So let's see what we've got. We're going to take in that equation and we're going to write down, we know that the average power of this light bulb, we've given it, we know that that's equal to V squared RMS divided by the R. And as I said to you just now, that's the equation on the data sheet. Make sure that you write it down and you now substitute the values. So what's the average power? Remember what I've said. In the question, we've been given average power. Whenever the rating is given, it's the average power. And we've been given the VRMS. So let's put the values in, and we're going to have not a difficult time with this. It's 100, and VRMS needs to be squared. Don't forget to square it. And it's divided by R. Now, we're going to multiply both sides by R and divide by 100, and we're going to get 220 squared divided by 100, and that brings us to our calculator. And there we go. We're going to say 220 squared, so let's square it, divided by 100, and that will equal 484. So the resistance of this bulb is 484 ohms. And that makes a lot of sense. It needs to be quite a high resistance because it's converting electrical energy into light and heat. Now, there's one further part of this question, and then we're going to wrap it up. We recognize that this additional appliance is connected across there. So there's another device, a big resistor, okay? You can call it a big light bulb. What's going to happen? I want you to see that if you connect something across it, it's going to draw more electricity. It's going to draw more current. And if it gets bigger than 10 amps, well, then you know what's going to happen? The fuse is going to burn out, and you're not going to be able to work it. So it's not advisable to overload a circuit. So bear in mind that these are important principles to look at when you're solving questions. Quick summary: an electric generator transforms mechanical energy into electrical energy. The AC generator that's producing alternating current has slip rings to make sure that the current is able to alternate within the circuit. It's not going to change them around. The alternating current direction changes, but the magnitude changes as well, and that's why we drew the graphs that are those sine and cosine graphs. Please remember that when you're given things in a question, you are given the RMS values for current, voltage, and power on devices. Guys, I've really enjoyed working with you today on these problems about alternating current. Practice, 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 and make sure that you keep a cool head as you go and solve questions on electrodynamics. We'll see you again soon.